Prakash Singh sir is Associate Professor in the Department of Electronics and Telecommunication Engineering at the International Institute of Information Technology, IIIT, Bhubaneswar. Sir has earned PA MTech in Microwave Engineering from IIT BHU Varanasi and PhD from IIT Kanpur. While teaching and research experience spanning more than a decade, Dr. Singh sir has been associated with IIIT Bhubaneswar since 2016. His research focuses on microwave and millimeter wave sensors, terahertz, frequency selective surfaces, biomedical imaging applications, where he has made notable contributions through publications in reputed journals and conferences. We are delighted to have you, sir, today with us, and it is our privilege to welcome Dr. Surya Prakash Singh, sir, to enlighten our participants with their expertise and insights. Over to you, sir. Thank you very much for accepting our invitation, sir.
Thank you, Shati, for such a nice introduction.
Thank you, sir.
One small correction. I'm not associate professor. Currently, I'm assistant professor. Okay, let me share my slide, and I will switch off the video right now to save the bandwidth. If any issue will be there, then I can switch on the video. Is it okay?
Yeah, it's fine. No issue.
Yes, sir. It is okay, sir.
Okay. My screen is visible to everybody?
Yes, sir.
Okay. Swati has already given a nice introduction of me, just related to this FDP program. First of all, I want to congratulate organizer for such a nice interactive sessions. And in this session, my topic will be terahertz imaging and analysis. The outline of my presentation will start with introduction. What is the requirement of high frequency spectrum, challenges at high frequency operations, and then we will move towards the terahertz imaging part. So I have segregated here in two parts. First will be free space imaging, and then will be a sensor-based, planar sensor-based imaging. So under this free space, we will deal with single layer multi-medium, then we will discuss multi-layer dielectric medium imaging. Then we will discuss some novel sensor based on spoof surface plasmon. And subsequently, we will discuss what is the requirement of spoof surface plasmon. So all of we can see that we all are surrounded with so many wireless devices. Like today's presentation is happening in online mode. Earlier, this was not the scenario. After the COVID, this has accelerated a lot. So when we all are connecting with each other with smart devices, definitely we all want that our quality of communication should be good. There will be no issue related to the transmission of my signal. So if number of users are increasing more and more, then there is a requirement of more bandwidth or more data rate at that time, so that we can experience better quality of communication. Whatever current 5G frequency bands are there, they are basically operating at 700, 800, 900 megahertz, 1800, 21. So up to 300 megahertz is there. But we all know that if we are predicting the future when the number of devices will be more and number of applications will be also more, then the current frequency spectrum will not help us to give a better communication. So the researchers are exploring higher frequency band. One idea is here, whatever frequency bands we are having at present, we can utilize them in a better way. So different techniques are there for better bandwidth utilizations, like memo technique is there, and multiplexing techniques are there, but they can help us up to a certain extent. They are not increasing the bandwidth, they are just increasing the usability of that bandwidth. So first thing is that if we want to cater higher data rate, then we have to explore higher bandwidth. So for that purpose, is researchers are exploring other frequency bands which can help us in our future communication. So like International Telecommunication Union has studies these frequency band 4.4 gigahertz to 4.8 gigahertz, 7.1 to 8.4 gigahertz, 14.8 to 15.35 gigahertz. Uh, Similarly, World Radio Communication Conference in 2019 has proposed these higher frequency band at millimeter and at terahertz frequency range, so that we can cater our future demand. But thing is that whenever we are moving towards high frequency, uh, idea is here we want to get more bandwidth, but it's not that much easy, because we have to replace all our hardware setup, which uh, will be compatible to those frequency bands. So what are the challenges when we are moving from low frequency band to the high frequency band? And what are the advantages we are getting apart from this higher bandwidth? So you can see when we are moving towards a millimeter wave and terahertz frequency spectrum, the advantage we are getting like a small wavelength, uh, because frequency is high. So if we know the fundamental relation that frequency is inversely proportional to the wavelength, or wavelength is inversely proportional to the frequency. So if we are increasing frequency, our wavelength will be small. The advantage of this wavelength, small wavelength, is that it helps us to get higher resolution when we are doing imaging of any object. So one picture is mentioned here. Let me use some pointer. So you can see here this picture. This is a terahertz image of a closed cardboard box containing several metal and plastic objects. So each of you can see here, we are very clearly able to recognize what kind of object is there by seeing the shape, and in our memory we know that what kind of these shapes are. So like keys is there, nut bolt is there, one pin is there, and one uh, paper holder pin is there. So that's the advantage we are getting when we are moving towards high frequency, because our wavelength is small. So we are our resolution is also getting better in terms of spatial and as well as in the axial resolution. In spatial, because the object, the transmitter area is very small, and in axial resolution increases when the bandwidth of the spectrum is high. The same cardboard box, if we illuminate it, if we throw a microwave signal and we study that reflected microwave signal, then we will not get such kind of fine resolution. So that's the advantage we are getting in terms of imaging. See-through capabilities, we know that when we are increasing the frequency here, there may be a problem of see-through capability here. Like when we are increasing and moving towards the visible spectrum, so light is not able to pass through that cardboard box. So whatever is inside, we are not able to visualize. But that's the advantage we are getting at millimeter and terahertz frequency. Another advantage, it's non-ionizing. Like someone can argue here that X-ray is giving very high frequency and it is giving more resolution. If resolution is our aim, then why we are not moving or going towards extreme high frequency like X-ray? But the problem at X-ray is there, that the energy, if we can remember our relation here, H equals to F into new here. No, so the energy associated with one single photon is directly proportional to the frequency. So if frequency is increasing, the energy carried by that photon which is interacting with the material is also high. So that's the problem with X-ray. X-ray is generally not recommended for human screening, like at airports. It is only used in medical cases. And doctor also advises that if you have done an X-ray today, let's say today, so they will not do again within a fine short time duration. They will recommend after 2 months or after 3 months. That's because whatever photons energy associated with X-ray spectrum is there, that's very high, and it is interacting with the biological molecule, and problem can arise at that time. So that's the advantage we are getting here, that it's a non-ionizing spectrum. So we can utilize for human screening as well. And one more advantage we are getting at terahertz spectrum here, that certain materials have terahertz signature. The meaning is here, like some explosive materials like TNT, PETN are giving resonance at very certain frequency. So whenever these objects are passing through that terahertz scanner, every time they will resonate at that particular frequency. So even if it is inside a card box or inside a bag, and if you are scanning with terahertz scanner, you will be able to figure out that what kind of material is passing through that scanner. So in many developed country, you will see terahertz scanners are deployed at airports for security regions, for screening of human beings as well as the materials baggage. So many advantages we are getting apart from this higher bandwidth. But at the same time, we are facing many challenges here, like device size and cost. When we are increasing the frequency, the device size decreasing, like in terms of antenna, if we talk about, then we have a lambda by 2 or lambda by 4 dimension of a antenna in loose sense. So if my wavelength is decreasing, so obviously the antenna size will also reduce. And when the size is reducing at that time, the cost will increase, because a specialized person along with the specialized engineering is required to fabricate that structure. High radiation losses are there at that time, means if whatever waveguide or transmission line we are utilizing to transmit these signals, at that time we are experiencing high radiation loss. uh, High absorption in the water, with the increase in the frequency, the losses of the water increases. So it helps, and it also restrict for biomedical imaging. Later on I will discuss how it is helping us and how it is restricting for exploring more and more in the biomedical imaging case. So I have shown here a few pictures of this imaging using terahertz spectrum and millimeter wave spectrum. So in the first picture, you can see here that a burned spot is there, 4-layer skin are mimicked here, and the signal is thrown. Then we are studying the reflected signal, and then we are plotting that reflectivity, or you can say the amplitude, maximum amplitude corresponding to that spot here. So we are able to visualize here the difference where the burned spot is there and where unburned portion is there. Similarly, in the bottom, one biomedical imaging application is there where a cancerous tissue is being detected compared to the normal tissues here. The difference between a normal tissue and cancerous tissue is that the cancerous tissue contain more water in it. So when we are throwing a signal towards cancerous tissue, so definitely if water is more, then the permittivity of that collective biological sample will be more. So if we apply simple electromagnetic theory, the reflection will be simple eta 2 minus eta 1 divided by eta 2 plus eta 1. So if your eta 2 is at higher side, then the reflection will be more. Got it? So the reflection from the cancerous tissue will be more compared to the reflection from the normal tissue. So, and if we are collecting those spectrum signals, and if we are plotting them and normalizing them, so definitely the reflection portion here, you can see here this red area, it's showing that it's different from the other area. So other area where the reflectivity is less compared to this one, so that's normal area, normal tissue area, and this is the cancerous tissue area. That's the simple way to do the biomedical imaging here. The issue I told you earlier, that this higher absorption of water is helping us, and it is also not helping us. It is helping us, you can see here that it's giving more reflection from those cancerous tissue area. But as we know that water is more absorber now for this terahertz signal, so the signal, when it tries to go inside the body here, immediately it will experience high attenuation, high absorption here. So the signal will not be able to penetrate beyond few millimeter, I can say. So it's very difficult to detect any abnormality in the biological sample if it is deep inside the skin. So that's why this terahertz biomedical imaging is mainly explored for the skin cancer, because at that time that lesion is at the upper body, and if it is inside, it's very difficult to visualize. The third case you can see here, one experiment was done by this P. Tevari group. They have taken one rat and they have given a burn mark to it. And then they have observed the reflection signal with respect to the time. So initially when it's uninjured, when no burn mark was given, then after 10 seconds, so after 1.16 second here, and then 7.11 second here. So thing is that if we observe burn condition, when burn happens, what happens? Immediately our body respond to that burn and it try to minimize the like minimize the uh, whatever we can say the damage. So water is coming to the surface where the burn is there. So when this initial stage is there, then water is immediately flowing towards the burn mark here. So that's why there is no clear visibility here where the burn mark is there, where the other portion is there, because throughout the body water is coming towards that side here. But if we give some time here, then we can see here if burn is more, then a bubble kind of blister kind of things comes out. So water contents in that portion basically where the burn is there, and the other portion remains means go to the normal state here. That's how, if we are doing the imaging, we can figure out here. So such kind of applications are possible. So these are different applications. So like one application is in the communications, like in this FDP, we are discussing this FSS one for communication point of view. So whenever we are trying to design any communication system for high frequency, then we have to fabricate all the things. Along with that one, we have to feed those modules with transmission lines or whatever waveguide mediums are there. So here is a normal PCB design layout. You can see what are you seeing here? Certain lines are there which are going and connected through the ground at the back end. These are lines very placed closely to each other here. So what are the problem at this time? If you have a little bit side. So if we have a transmission line and which is at open-ended, or if it's not terminated well, then there is a possibility of radiation from that transmission line. If if we bend a transmission line, then we know the basic theory of electromagnetic theory, that this discontinuity will try to radiate the signal here. So you can see here so many bends are in this PCB. Sometimes it is not properly terminated here. So it will cause the radiation. And when radiation will be there, then there will be loss of power, whatever signal you are sending towards the load. So that's one issue, that high radiation loss we are experiencing. That's the reason microstrip lines are not preferred at very high frequency. We are exploring different kind of transmission structures or waveguide structures like SIW structures. Okay, so one problem is high radiation, another is poor isolation. Isolation, you can see here, when the transmission lines are very near to each other, then the signal can leak from one transmission line to the other transmission line, because both have the same wave momentum and same velocity of that signal here. So there is a high chances that signal may leak from one transmission line to another transmission line. So it is give a poor isolation. Non-immune to the external interference signal here, because if any free radiation is coming and from any other module in your design, then you can see here, we know that quasi-TEM mode is there in this microstrip line, which is similar to the TEM mode. No? So if any TEM mode signal is coming, then that signal can easily interact with this transmission line, and it will hamper your signal integrity. So these are the challenges when we are moving from low frequency to the high frequency. So apart from that one, whenever we are fabricating any device like antenna, filter, or etc., so we are using the substrate material or any other kind of material, like in the radar we are using radome. So we should know what is the material property at that frequency at which we want to design that particular component here. So that's the reason we want to explore the dielectric property of or whatever materials are there. So I'm now going to explain in next slides that what could be the possible way to detect the material property, so that we can utilize those materials for our applications, and we can also utilize them for imaging purpose. So before we go to the methods here. Let me explain a little bit in a very brief way how the terahertz generation and detection system take place here. So this is one kind of system where you have a photoconductive antenna, which is derived from the laser beam, and it gives the terahertz signal, and that terahertz signals we are focusing with the help of these kind of focusing lens and the beam splitters here. Then we are again detecting at the photoconductive antennas here. This kind of setup is very costly. So most of us experience this thing when we are thinking to work in the terahertz zone, that we are not getting measurement facilities. So what should be option at our end here? One option is here that if we are not going to get such kind of measurement system, another kind of measurement system is this one, where you have the VNA, and normal VNA, we can use the frequency extender. Like suppose you have a normal VNA from 100 hertz to 20 gigahertz, you can use the frequency multiplier, or you can say frequency extender, to enhance that particular range. So here it will work as all of you are working in that domain. So all of you know that VNA is giving continuous frequency spectrum. So from this, we will get a continuous frequency spectrum at higher frequency. But still, the cost is very high if we compare with the normal or with the low frequency operation. So idea is here that first we can explore the things in the simulation using electromagnetic simulators like CST, HFSS, and we should mimic those simulation settings such that it is mimicking the actual measurement scenario. Then only you can convince other that okay, I don't have a measurement system, but whatever simulation settings I have done, it is very much similar to the actual measurement system. And then you can convince other one. Apart from that one, if someone is having access to the measurement facilities through friends or through any means, then you can show your simulation result. Then they can be also convinced, okay, you are getting some kind of good results. So now we can extend a helping hand to that particular person to use the measurement facilities, because nobody give access to such kind of measurement facility easily, because they are very costly. if any issue comes, then there is a problem. So here is a measurement system for a single layer material here. So you can see here we are trying to mimic the actual measurement scenario where a terahertz transmitter is there, beam splitter is there, material under test we are putting here, and then a terahertz receiver is there. Signal will travel from here to here, it will go interact. In between, it is hitting this beam splitter. So some part of the signal is going in this direction. And then it's again coming back here. Some part of the signal will go in that direction. So total length, if we consider here from here to here, let's say it's L1, and from here to here, it's L2. Then let us see what happens to my signal. Let my initial signal at this particular point is source signal. So let me call it ES. It's an electric field signal here. So signal in this laser based kind of terahertz system, whatever signal is coming, that is directly giving you the electric field signal here. So let's say the electric field signals just after this transmitter is ES. So it is traveling that much distance. So that much delay will experience here. So we can write here the frequency domain equivalent here, ES along with this delay, exponential minus j omega. And the signal is traveling in the air only right now. So under root of epsilon air L1 by C. Then you can see here it is hitting this beam splitter here. So because of that one, there will be some change in the magnitude of the spectrum. So that coefficient we are multiplying d1 to mimic the actual measurement scenario. And let's say my reflected signal is my ER1, the first reflected signal, which is reflecting immediately from the surface. Then second reflection will come because some part of the signal will go inside and then it will get reflected from the second junction of this material under test. So this will become ER2. Similarly, some part of the signal will again reflect here and then it will reflect here, then the third signal will come back here. That's how you can get multiple signals here, and we can separate through time window and we can process those signals here. So ER1, if we see here, so ER1 will be whatever signal is coming at this particular point. So at this particular point, signal is coming your E in 1. Along with that one, whatever reflection coefficient is between medium 1 and medium 2. Medium 2 is the material under test, medium 1 is the air here. So R12, what is the reflection coefficient when my signal is going from medium 1 to medium 2? We can multiply here. And along with the second time when my signal is crossing this beam splitter, so again there will be change in my signal. So what is the effect of this beam splitter? Let the coefficient is my B2. So and the total length traveled by these signals extra from the earlier one is this length L2 here. So we can again multiply with this one along with this EN. EN is already there. So you can see very easily we can write or we can get mathematical equations that how my field is depending on these things here. Similarly, you can write ER2, ER3. And if we do some kind of mathematics jugglery here, if we multiply ER2 divided by ER1, then again ER2 divided by ER3, because my aim is to figure out what is the electrical parameters, electrical constitutes here, that epsilon and mu. So right now we are dealing with the dielectric, so mu will be 1. We are only interested in the epsilon value here. So that we are arranging these equations such that we can get rid of the unwanted things here. So you can see here a very nice expression we are getting here. T12, T21 divided by R12, R21 here. T is the transmission coefficient from 1 to 2, 2 to 1 medium, 1 to reflection coefficient, and T is generally defined transmission coefficient of twice eta 2 divided by eta 1 plus eta 2. So we can utilize, and eta is defined as under root of mu by epsilon. So mu is 1, so directly up, this eta is depending on the epsilon. So you can see your whole equation is now where, because these are the measured quantity, this ER2, ER1, ER3, these three signals you are able to do the measurement, you are able to separate them, you are able to process them. And when we are doing such kind of things, we are getting this product X. So this X is a known quantity here. And now we can replace this transmission coefficient in terms of the unknown parameter of the materials here. And from there, we can get this equation. And if we rearrange these equations, we can get our epsilon MUT. So X is known. Based on that one, you can get your MUT, means permittivity of the signal. So you can see here, we have started our measurement in this setup, whatever actual measurement setup is there. But at the end, we are seeing that it is not depending on the beam splitter coefficient of B1 and B2. It is not depending on the length at what place we are putting this transmitter and this receiver. They are canceling each other here. Okay, so now we can simplify our things here. So we can remove everything here. For our simulation purpose, we can decide one plane from where we can excite our signal, and then we can receive signal at the same points, the received signal from first interface, from the second interface, like this one, and we can analyze those signals here through simulator. So that's the way you can do, or you can start your research work at high frequency using numerical simulations here, even if you don't have the actual measurement setup. Thing is that you have to mimic your actual measurement scenario, and then you have to rethink your model. So you can see here a numerical simulation model is there. So simple thing, at the back, one time metal is there, one time metal will not be there, air is there. You can see here, this is not depending on the other material, which is after this material here. No, only air and MUT is there, air the one here. But sometimes we find a case like in your substrate, if we remove the metal part at one end and other end, we can keep the metal part here like normal FR4 substrate. And if you before fabricating your antenna, if you are interested that what is the dielectric constant, actual dielectric constant of that substrate you have in your lab, so you can perform this kind of measurement here to get an idea about the epsilon value of that one. So no need to remove metal from both sides. Okay, you can keep metal at one side, and other side you can remove the metal. After that, you can do that measurement here. So in that way, it can help us. So these are different materials taken for the simulation purpose here. And these are the measured complex permittivity taken from literatures here. So same kind of permittivity is given during the simulation. We are exciting the signal from this port, and at the same port, we are receiving the signal here. Okay, so you can see here different signal scenario here. First one, SDP sample is there. It is tested for both case, when air is at the back side and when metal is at the back side. One advantage at the metal at the back side we are getting here, because if air will be there, then the reflection from this side will be small. Okay, so first signal will be good, second signal will be good in strength, but third signal may not be good in strength here. But if metal is there, then because of the metal, because reflection coefficient of the metal is -1, so it helps us to get a good strength in my third reflected signal here. So same thing you can observe here. The first signal here, the second signal in both background scenario, but the third signal in case of air is very small in magnitude, but in the metal it's having a good amplitude here. And it affects the our extracted epsilon value here. You can see here this third signal ER3 is in the denominator. If this value is going at lower side here, if it's very low, then tending towards 0, then it's difficult to get a correct value for X here. Okay, so and from X we are getting this epsilon MUT here, so that error will propagate here. So same thing you can observe here. When your sample is bagged with the metal, then reconstruction or the calculated permittivity value is much more near to the actual value here. Same thing you can observe here, this red color air bagged, blue color metal bagged here. Okay, so air bagged, there is more fluctuation in the value here. In this case, this pink one, more fluctuation is there. Similarly here, you can see here when the sample is metal bagged, it's a lossy sample. So obviously when losses are more than the multiple signals which are coming after the first and second one, it will be very small. So in terms of the air bag signal, it's small. So because of that, one error is more, and it's so next thing is that if you want to improve the accuracy of your extracted parameter here, we can use the optimization after that one. Already we have the initial guess which is close to the actual value of the permittivity here. So after that, if we are applying an optimization, every time you will get your solution will converge and you will get the correct value of the optimized one. So you can see here that when we are using the optimization techniques here, this simple formula we are using here. Based on that one, we are extracting a gain here. So now it's very refined value here, you can say. This for better visualization. This was the earlier extracted value when there was no optimization. And now when optimization technique is applied, then there is the extracted one here. So error is now less in the extracted part here. So one idea you can see here, we can use the reflection signal to extract the permittivity of a material here. Second thing, as we can see here, the getting third reflected signal is very tedious, very difficult one. The amplitude reduces if your material is lossy. So what we can do here, instead of going with all reflection signals, we can use some reflected signal, some transmitted signal here. And then we can process those signals to figure out the permittivity of your material here. So this is another method to extract the material permittivity here. Along with that material permittivity, you can also figure out what is the width of this material under test. Because what happens at high frequency, even a small difference in your measurement here, suppose you have done the measurement for the L of material under test, and if there is a small error in terms of fraction of millimeter, but it will create a problem on the extracted parameter here. So the idea is here, instead of doing any physical measurement of the length of the width of the sample here, we can extract this width from the measured signal itself here. So that's why we are calling it imaging, where we are not only finding the permittivity, along with that one, we are also finding what is the depth of this particular sample here. If any question is there, you can ask in between as well.
Participants, if you have any query, you can please drop in the chat box or raise the hand.
Because my slide is in the full screen mode, so I will not be able to check, I think.
Okay, sir. I will tell if any question will come,
Yeah, if
sir.
any question is there, so it will be good if it will be interactive from both sides.
Okay, sir. I will tell.
Yeah. So you have seen that there was a problem in the third reflected signal. That's why we are proposing the second way to figure out the permittivity here. So in this case, my signal is going here, it's hitting the sample. So first signal we are collecting here, there was no issue in the second reflected signal. So we are only restricting up to first two reflection signal. And similarly here, two transmitted signal we are collecting here at this side here, at the other side of the sample here. And then we are processing these ER1, ER2, ET1 and ET2 here. And now you are now you have an idea how to write the electric field equations for ER1. So you can write simply ENINT, what is the reflection coefficient here in terms of this one, you can write here. That's why I have not written those equations, but we can write here. Then what is the reflection from air to material here? So R12 we can write here. Along with that one, the signal is traveling this distance L1 here. So exponentially, we can write here the delay exponential of e to the minus j omega of L divided by C here. So here L1 is there. Similarly, ER2 you can write here, ET1 is right here. In ET1, there will be two transmission coefficient from medium 1 to 2 and then medium 2 to 3 here. Then ET2 you can write here, and then you can rearrange the equations here. So equations are rearranged, and again we are getting a simplified relation here, that T12 T21 divided by R12 and R21. Now again, T is the transmission coefficient twice eta divided eta2 divided by eta1 plus eta2 for T12. Similarly T21, so it will be twice eta1 divided by eta1 plus eta2. And then you can replace your eta as under root of mu by epsilon. So this P will be known quantity because we are measuring these electric field signals. So all four quantities are known to us here, means P is known to us. And then we can replace this transmission coefficient and reflection coefficient in terms of material parameters. And then we can solve these equations to figure out what is the epsilon MUT here. Okay, so that's how you are able to figure out the complex permittivity. Once you know the complex permittivity of the sample, so you can consider any two signals here, either reflected signal or the transmitted signal. So you can see here what could be the delay in these reflected signal ER1 and ER2. Let's say the signal ER1 is received at time T2 and this ER2 is received at time T2 here. So the delta will be here, delta T will become T2 minus T1. So, and how much delay we can see in this picture? This delay, because signal is going inside and it's sitting back, it's coming back here. Means it is traveling twice L length here. Okay, so we can write simple relation of velocity of the signal in that medium. V will be here twice L divided by of delta. I'm interested on this L here. So L will be here Vp multiplied by delta T divided by 2. Vp is the signal here. Signal inside this material. Our the way of interaction is in the TM mode here. So we can write here C divided by under root of epsilon of this particular material, epsilon m multiplied by of this delta T divided by 2. That's how you can calculate your width of the material. So you can see here, no need to do the measurement for this L value here, because if you are doing the measurement at and you are doing the experiments at very high frequency, chances are there human error will be there in this measurement. And because of that one, if you are doing any or calculating your epsilon based on the L parameter, then that error will propagate. So here we are calculating them separately. We are calculating with our measured signal only. So again, a scenario is here in measure in the simulation settings here. One transmitter port, here is another port 1, port 2. Here we will receive the reflected. At port 2 we will receive the transmitted signal here. So these are the signals here. Then we are separating those signals through time window here. Then we are taking the Fourier transform of those signals here, and then we are processing according to that derived relation here. And then we are getting our extracted permittivity. So you can see here, this time this extracted value is almost identical or almost same as your actual value during the simulation here, because the error which was coming in the extracted parameters during the earlier method was because of the low amplitude of the third reflected signal. So right now that's not the case, so error will be less here. You can see here these are the extracted permittivity value without any optimization. Even if you want further optimization, you can utilize the any kind of optimization techniques here. You can already you have the permittivity values with you, and which is very near to the actual value here. So always your solution will get converged and you will get a very refined value after the optimization. So this is the case if you are interested to figure out the permittivity of any sample which you are going to utilize for your higher communication applications. So it's always good to know what is the permittivity of your materials. Multi-layer case now. So single layer case we have seen. Multi-layer case, like in the introduction I have seen, if inside the card box you have certain objects, and if you are interested to figure out that what is the shape of that one, immediately you can throw the Terahertz signals, you can draw the reflectivity plot, and you can visualize that what kind of object is inside. So here idea is here, instead of means along with that, if we know the shape, but sometimes we have seen that people try to get illegal things giving the normal shape, but actual material of that object is very different one here. So can we guess what is the material or what is the electrical parameter constitutes of the objects kept inside any multi-layer in a multi-layer systems, like inside the bag? If object is there, so it's kind of a multi-layer system. So the bag thickness means bag materials, then you have to decode what is inside. So can we, along with the shape, can we figure out what is the permittivity and the permeability of that material which is kept inside that card box or inside a box? So let us see how to decode that one. So let us take a multi-layer system here. So let's say we have a 3-layer multi-layer system here. Material 1, material 2, material 3. Each one is having different width here, L1, L2, L3. So again, here we are starting with the actual terahertz measurement system setup here. This time, first we are putting a metal plate to get a reference signal here at this particular point here, RR dash here. So if any signal will go here, it will travel to this part, it will go back, it will hit, and it will come back here. So that will become your reference signal here. Second times, when we'll remove this metal plate here, then the signal will go, it will hit the first junction which is being formed by the first material and the air, then it will go back here. So that becomes your first reflected signal here. So we can easily write the electric field equations corresponding to these reflections here. Second reflections will come here when the some part of the signal will go inside, and then it will come back here. Then third will go here like this one. Fourth will go here and it will come back. Okay, so when it is coming back, it is transmitting from medium 3 to 2. So T32, then T21, like this one. When it is going in this direction, then T12, T23. So these transmission coefficient and reflection coefficient, we need to take care of that. And then you can easily write the electric field equations. So here, for various collected reflected signals at this receiver are written here. And then we can rearrange these equations here, and from there we can get the different value, like here R01, and this R01 is nothing but the reflection coefficient when the signal is going from air to medium 1 here. So we know here that we can replace in terms of the epsilon air and medium 1 permittivity here. So if we are able to know R01, then we are able to get what is the value of the permittivity of the first material here. That's how you are able to get it. And once you know it here, you can figure out what is the width of that particular sample here. So these are the equations by which you can get all these things here. And as already we know that here the signal is traveling through multiple mediums here. No? So your signal strength will be very small. So whenever you are calculating at the first hand using these equations, the error will be more. After that one, you have to always utilize the optimization method. How to do it in the simulation one here? Because all of us struggle to get the measurement facilities. So you can start with the simulations one here, and then you can go for the measurement here. So see here, first scenario, first we are putting a metal plate, we are collecting the reflected signal, then we are removing the metal plate, figure number B here, and then we are collecting the signals from different junctions here. And these, so in the simulations, these are the signals we are collecting here. And then we are calculating what is the permittivity of each material. So you see here, the difference between T1 and T0 will give the width of first material. Difference between T2 and T1 will give the difference width of the second material. So already from the figure, we are able to know what is the time delay, at what time in the actual measurement system, at what time we are collecting the signal. So we can calculate the delay. From there, we can calculate the width. So it's actual scenario. So here you can see, as I told you, because we are getting multiple reflected signals, which are coming after so many reflection and transmission. So the amplitude is less here of the collected reflected signals here. That's why the error seems to be more here everywhere. No? And if it is materials are very lossy, then the error will increase. So after that one, you have to use the optimization. So I have not shown the optimization method and the end results here just to save the time. But you can do always do that one. So from here, you are getting the initial guess, and then you are getting the optimization to get refined value here. So this multi-layer problem or multi-layer understanding can be extended for biomedical imaging, for security screening, and so many applications here. So like here, I'm going to present a case of skin, and then we will discuss normal skin and then the infected skin. So how to mimic the actual case in our simulation settings here? That's always a issue. So for that one, always you have to see that what is happening in the actual measurement scenario or what is the actual case. So through literatures, you can get very good idea about the permittivity of the skin, how the water profile is there, and based on that one, you can generate your skin model. So in the literature, you will see various authors have presented various models for the skin, because model will not be unique. Model is always to mimic the actual scenario. So it will be different for everyone. So from measure one of the measurement setup, I have taken this water profile, that what is the average water profile in a person from upper skin to the inside one here. So actually the starting, if you will see your skin, it's a layered one here. The first layer is generally known as the stratum corneum, then the epidermis, after that one, then the dermis. Now, generally this stratum corneum is around 8 micron to 15 micron or 16 micron. Similarly, epidermis is around 50 micron to the 100 micron, and then dermis is extending from that beyond up to 2 mm. After that one, other biological material, fats and etc. will come into the picture. So as we are discussing here, this skin cancer issue, because we know that our terahertz signal will not be able to penetrate much deeper inside the body. So we are not interested what is the material, what is the biological constitute in very deep inside. So we are only mimicking the skin here. So this is the actual water scenario here. So for creating this model here, I have taken an approximate, means intermediate water profile here. So this one, very easy way to represent the actual one. After that one, the water profile in the actual scenario is always saturated here. After that one, it's not changing water content. So a simplified profile of this water hydration we are taking. Then we are mixing this water hydration percentage with the dry skin. And so for dry skin, people have given the uh, permittivity value here. So we can use the mixing formulation, that if we are mixing this water with the dry skin, then we are getting the actual our skin content here. So in one paper, it was given 2.1, in another it's 2.5, 2.7, like this one. So we are taking here as a 2.4, that average of several papers I have taken. Then we are using a mixing formula. You can see here also why I have again 3 different layers of skin is there, but in those 3 basic skin layers, again I have taken change in the material here. Why? You can see here water profile is continuously changing within every 2 micron, or you can say the every micron distance here. Water content is continuously changing and it's stabilizing after 40-60 micron here. So if you are directly taking the mixing formula for one single layer of this stratum cornea, then throughout this 14 micron, your permittivity will be same. But this is not the actual case here. In actual case, your water content is changing, so your permittivity of that skin will also change with every micron. Okay, so that's why we have taken here 2 micron thickness. So again, we have taken layers in this stratum corneum, is given 7 layers. This 36 again 2 micron distance we are taking mean one, that after 2 micron second my permittivity is changing. That's the way we have modeled here. So you can see here we are using this mixing model here. So we have 2 materials with 2 volume percentage here. So epsilon of your dry skin, then epsilon of your water. Then we are mixing these 2 materials to mimic the actual skin scenario here. So from the papers, the permittivity value of water is taken here. So you can see here, once this model is done, and then we are illuminating it using a one port here, and then we are collecting the signals here. So we are getting this reflectivity. So you can see here, this red one, is calculated reflectivity from one standard paper given here. This is the measurement given by this Emma Pickwell, very known person in this terahertz imaging in biomedical case. She's from Britain, UK. She has done a lot of work in this terahertz domain. So she has done several measurements, and in one of her paper, she shown that this is the actual measurement reflectivity from 100 persons. This is the average reflectivity from that. So our model is very close near to this measurement compared to the model presented by this group Bennett one. So from here, first of all, whenever you are presenting any model or any simulation settings here, one idea is here you have to mimic your simulation settings such that it's near to the actual measurement scenario. Another thing is that it's better to match it with some already published data. So it will give you confidence that whatever you are doing in a right way. So here first we have mimicked the skin profile here, then we are collecting the reflectivity, and then already we have the reflectivity profile from measurement from different models given in literature. So we are comparing it here. So after that one, we are sure that whatever model we are presenting, it's very near to the actual scenario here. Then we will move to the our application scenario, that once you have a skin model for normal skin, then we know that the difference in the cancerous skin and the normal skin is that in cancerous skin the water content is more compared to the normal skin here. So you can see here for normal this basal cell carcinoma in one paper, and through measurement only this is given. These parameters are derived here. So we can utilize these parameters, we can put it here, and then we can use this mixing model, and then we will get the cancerous skin scenario here. So what we are doing here, we are taking 2 different cases. one normal skin case. In another case, we are assuming that the skin is cancerous and it is up to here 1 into 10 to the power minus 4. So we can write here 100 into 10 to the power minus 6 here, means we are assuming that first 100 micrometer is my up to 100 micrometer depth my skin is cancerous here. So if I'm throwing my terahertz signals at two different places, one is the normal skin, another one is the cancerous skin, what should be my reflectivity, and based on the reflectivity, can we predict that this is a cancerous one or abnormal skin and this is the non-normal skin? Along with that one, if we are also able to reconstruct the imaging, this permittivity profile, it will be addition to that one here. So earlier, people have only shown the change in the reflectivity compared to the normal skin and the carcinoma skin here. So in our case, we have shown the change in the reflectivity along with the change in the permittivity profile as well. As you can see here, when the permittivity profile is different, means the cancer in the normal case, epsilon 1, epsilon 2, these values are different. And here in the cancerous case, this is different here. So permittivity profile is changing because the water content is changing. Water content is changing means permittivity profile of that water is changing. So we are mixing with the dry one, so that is also changed here. So if we are able to reconstruct the permittivity profile, then we can also get an idea about the uh, abnormality here. And already we have seen the multi-layer case, how to get the permittivity as well as the depth of those or width of those materials here, multi-layer case. So we are utilizing that thing now. So we have taken two cases here, normal skin case and the infected case here. Then we are utilizing these reflectivity signals here, plot here. So you can see the reflectivity from the healthy skin is less compared to the reflectivity from the cancerous one. And it's a very normal case, no? Because if skin is cancerous, more reflection will come because water content is more. So reflectivity will be more here. You can see here reflectivity is more compared to this one, normal tissue. Now we are reconstructing the permittivity profile as a function of the depth here. Because if your doctor is able to know that up to what depth your cancerous tissue is there, then it will help him or her to do the surgery. If he or she is not known to the depth of that cancerous tissue, so based on his or her experience, he will remove that skin. So why to remove your healthy skin if it's not required? So if they have a better idea about the depth profile of this cancerous tissue, then it will be good here. So that's the reason to represent this permittivity profile with respect to the depth here. You can see here. So if a normal skin is there, so permittivity is less, and then it is going more and more, as we already know the permittivity profile or the water profile here. The water profile was going like this, so permittivity profile is also following the same. No, so here if we are reconstructing here, the same thing we are observing here, that permittivity start with the lower one, it's going towards the higher side here. And here in this case, in case of BCC, it start with the high and it's going to the normal skin layer here. Second application here, the burn case. Like in the previous exam, means when we have started our presentation, then I have shown one picture where the information about the burn mark was there. So when any burn is there, doctors are categorizing in three different first degree burn, second degree burn, and third degree burn. Every burn has its own characteristics here. If first degree burn is there, means a very small burn is there. So what you experience here, normal water oozing will be there towards the outer surface of the skin, and after sometimes it will settle down. If it's a second degree burn here, then the blisters will come out. And if third degree burn is there, then what happens? The upper skin completely get dried, it's charred one, and then below that one you get the water here. So you get two layer kind of model here. So in the first case, if it's is there any acceptable limit of permittivity? Can you read that one?
Sir, actually, I want to know that the permittivity for the infected it falls and for the healthy it is rising. But is there any limit that the range should be in this particular range, the permittivity of healthy skin and the tumor?
Yeah, you have to see what are the permittivity values are given in the different literature. So you can take a average value of that one.
Average, okay.
Yeah.
Okay, sir.
Okay, so you can always take an average value of that because it's changing person to person. Skin profile is different for every person. So it will not be a fixed value. It will be in a range. So through the literature, you have to see what is the range given there.
Okay, sir.
Okay.
So one more question is there.
Yeah.
Sir, it may be possible that other things also change the dielectric constant of any body cell. It is
Yeah.
not only with the water content, then
Yes,
after sensing.
it's not only because of the water content, but water content is the major portion. Along with that one, blood cells will be there, protein cells will be there, fat cells will be there. Okay. So thing is that you can't include all those things in your model. Your model will be very difficult. Okay, so when you are doing the simulation settings, you have to see how you can remove the complexity of your model.
Okay, sir.
It's always better to include more parameters there, but it will complicate your model. That's why in the previous structure, I have shown you that after giving the model here, we are comparing the model, our modeled result with the measured one. And this is also the red line is also the measured one, means modeled one. But see here, it is far away from the actual measurement scenario. But that model is also acceptable. They have removed certain parameters. They have not considered this case. They have not considered this case here. They have only taken three layer medium for the skin: stratum, epidermis, and dermis. And you can see here water profile is continuously changing with respect to the depth here. Every microsecond is changing. So it's better to mimic that one. They have taken up to this distance, up to stratum corneum, no change in the water content or no change in the permittivity. Let's say we don't want to say the only water content. So all the biological content here. So they are saying that up to this length, it's not changing at all. Then again, it's changing. So it's not a sudden change, it's a continuous change. So you have to include in your model. That's why the permittivity reflectivity results is very close to the average reflectivity coming from the measurement. You can also include the blood cells scenario. You can include the fat, proteins, etc. in your model, but it will complicate your structures.
Okay, sir.
Okay.
Yes, sir.
Same here, like here. We are taking the first degree burn, then the second degree burn. So in the second degree burn, everywhere mostly water is there now. Okay, so that blisters here. So it's filled with the water. So water is the main constitute there. So it can be represented as a single layer model. No need to use a different means multi-layer model here. But in the third degree burn, we know that the upper skin is completely burned and it is totally dry, and the water is below that, and then the water is there. So you can use a double layer model here, and it's not taken random. Always you have to see the literatures, how the measurement results and how the researchers are proposing the actual scenario. Based on that one, you can give your model. So here, stratified media model for unburned and first degree burn. So the only change in the first degree burn and the unburned is the water profile. Earlier, it was taken, the water content was taken, that is changing from here around 30 here 30% is, then it's coming down, then it's going up to around 70% here. And when water content will be more, so instead of starting with 30, you can start with 35. You can take that this is the model for my first degree burn here, like this one. Little bit water is increased, more water is not there. But in case of second degree burn, from top to bottom, water is all everywhere, water is there, those blisters, so water content is around 90% here throughout the skin. Okay, so there will be no variation because the skin material will be in negligible. Maximum portion is the water. So you can, and permittivity of water is much higher compared to the skin one. Dry skin material permittivity is only 2.4, but at the same frequency, the dielectric material of the water is around 60. So you can neglect that one because here volume is more, permittivity is more of that water compared to the dry skin. Okay, so that's how you have to think. So single layer model for the second degree burn and the third degree burn here, and then we are analyzing here. So we are not only analyzing that whether it's a burned skin or a normal skin. We can also differentiate between various degree of burn here. So you can see here in the model, we have taken all these scenario here. So first degree burn, second degree burn, third degree burn. So in the first degree burn, water is more compared to the normal one. So normal one, you can see here in this intensity profile here, this blue color is the normal one. Compared to that one, it's a blue. Little bit water is there, so intensity is more compared to that one. And in the second degree burn, water is very high, so here the reflectivity will be more compared to the first degree burn here. But in the third degree burn, the upper layer is the dried one. Okay, so the reflection from the first layer will be small one, and the second layer is going inside, then again it's coming back here, so that signal strength will get reduced. So compared to the first degree and the second degree burn, the reflectivity from the third degree burn is low. And along with that one, because it's a double layer model here, so signal is coming from here and then it's coming from here, so there will be difference, or you can say we will get two reflection here instead of this case where a single reflection is coming, and here also single reflection is coming because it's a continuous profile, so it is not experiencing that there is a junction between the stratum corneum and epidermis and between epidermis and dermis. So you will not experience any multiple reflection scenario, but in this case you will experience that one, and that's the thing we have reported. And in the third degree burns, if you are throwing a terahertz signals, then there is a possibility that you will get a second signals here which give an idea that it's a third degree burn. What happens when a person is burned and it is and he or she is being treated, some wrapping is there to heal that one. So every day you can't remove that one. Based on the experience, they are giving the time and they think that now it is being healed, and then they are removing that treatment. But thing is here that if we have a mechanism from where we can get to know that how my skin is healing with the time, so from outside we can throw the signal and it will be a multi-layer scenario where the bandage will be there, below the skin will be there, and then there will be water profile here, so we can get to know this multi-layer scenario, and with respect to the time how this reflectivity signal is changing and how my permittivity profile with respect to the depth is changing. That will give an idea. When my permittivity profile goes towards the normal skin here, then we can say my healing is going in a right direction. So no need to remove the bandage on everyday basis or two-day basis to get to know that how my wound is healed. So that's the idea. Okay, so we have seen the scenario of imaging here in free space. Suppose someone is interested, someone can say every time we are not encountering with applications where we have to do it in the free space scenario. Instead of that one, we can use a normal planar sensors. So can we use it here? So first thing is that we have to see what are the things available at high frequency. What can we use the same setup we are using at the low frequency, like your microstrip line. We have seen what are the problems coming at the microstrip line, so we have to move for other transmission line. So you can see SIW we can utilize here, and then we can use SIW transmission line to feed my sensor network here. But certain disadvantage at SIW is there, although it's very popular at the high frequency, that dielectric losses are more, metal losses are more. If we are increasing the frequency, we know that with the increase in the frequency, losses of the material also increases. And here the signal travels through this dielectric substrate along with the top and bottom metal layer here. So when the signal is traveling through this dielectric material, obviously your dielectric losses will be more, and metal losses is already there. And we are using the VIH to give a shielding for my signal, so that my signal should not leak through this wall here. But when we are increasing the frequency, the possibility is that your signal may leak through these VIH here, so there will be radiation losses as well. Okay, so there are certain limitation with this substandard DGAD. So people have proposed different waveguide, dielectric rod waveguide. Also, one problem is here, it takes a lot of space during the design side here. And we have to design it very carefully so that we can minimize the losses through these VRs and etc. If we want to feed any signal to multiple modules here, see the space taken by this power divider is very high. So that's the problem with SIW here. Another idea is dielectric rod waveguide. We can utilize these kind of waveguides at high frequency, because now we don't have a metal, so that metal loss will not be there, but dielectric loss will be there because signal is coming inside. Dielectric losses can be minimized if we are using a very low loss kind of substrate. So those will be very costly. But another problem is here that they are not planar in nature. So it is very difficult to connect these kind of waveguide system with another module here. If any other module is here like M here, then it's very difficult to connect that module with this transmission line. That's major issue. So can we come up with or do we have another arrangement for high frequency? One concept is there of spoof plasma. Before going into the spoof plasma, let us discuss the fundamental of surface plasma. What are the surface plasma? Collective oscillations at the metal and air surface or dielectric surface here. So one scenario is given here. Your signal is traveling along this surface here. Okay, so your signal, because the metal is here, so no electric field will be in this XY plane. Okay, because tangential field will be 0, means your EY component will be 0, only possibility of EX component and EZ component will be there. So accordingly, we can write the equations and we can figure out what are the conditions for generating a surface plasma wave. So certain theory is given here, like what is plasmon frequency and what are surface plasmon and how the surface plasmon is traveling here. But I'm interested in this mathematics right now, which will give an idea that what are the conditions we need to satisfy to get an surface plasma, and then we will see what is spoof surface plasma. So as I told you here, that your signal is traveling in this direction and in this z direction. No electric field signal can exist in the y plane because your metal is extending in this xy plane. So you can write here your field E1, that EX component is there, EZ component is there, and propagation constant is in both direction, Z and X direction, positive Z direction, positive X direction, along with this harmonic component of Ez. Omega t corresponding, the magnetic field can be written here. That's for Z greater than 0. Then similarly, Z less than 0 you can write here. Then you can put the boundary condition and you can get these equations here. That kx1 is equal to kx2, so you can write kx here, and another equation is here for the z direction. It's an interesting one here. If you can write here, then I can write here like equals to with the minus sign. Propagation constant will not be negative. Kz1 and Kz2 both will be positive. Generally, epsilon D, dielectric constant value, is a positive one here. So it is a positive one here. If we want to satisfy this equation, then definitely the epsilon M should be negative. Means the permittivity of the metal should be negative if we want to generate surface plasma wave in our metal dielectrics interface here. And can we get it here? Yes, because this permittivity of metal is defined by this relation, Drude model. It says that 1 minus omega p divided by omega p square, where p is the plasma frequency here. So you can see here, if omega is less than omega p, then what will happen? This overall value will be higher than 1, and you can get epsilon m is negative. If omega is more than that 1, then epsilon m will be positive. So if your operating frequency is less than the plasma frequency, then there is a possibility that you will get the permittivity of the metal in the negative side. And if you are getting it here, then you can generate the surface plasma here. That's the fundamental concept here. Based on that one, again, you can further simplify here to get your propagation constant in terms of these permittivity values here. And from there, we are getting a table here that under what scenario we will get the propagation and what kind of propagation we can get here. So based on these one, if my kx is real, kz is real, epsilon m is real, then we are calling it a Brewster mode. Right now, we are not interested on that one. We are interested on this particular mode, propagating spoof plasma mode here. This is coming here when my permittivity of the metal is negative. At that time, my kx is real. My propagation is going in the x direction, but no propagation is going in the z direction here. So we are suppressing the propagation in the z direction. We want propagation along with this metal and dielectric phase. So for that one, we are satisfying this equation. If we are able to get it here, then we are able to get the bounded propagation here, which the signal which is bounded to this metal and dielectric interface only. The signal is not traveling in the y direction, signal is not traveling in the z direction. Even if it's trying to go in the z direction, because it's imaginary here, it will die out quickly here. So if we draw the dispersion diagram here, very interesting dispersion diagram we are getting for this kind of surface wave here. Initially, you can see here, it's a omega versus k diagram here. Initially, if we see the velocity of my signal Vp, then it's a delta omega by delta k. Initially, it is 0. Then it's increasing here, because if we take 2 points here, we will get delta omega from here, we will get delta k here. If I'm choosing another points here, I will get Vp value here. So see here, the velocity of the signal is increasing, but after that one, it's slowing down here. K difference in K is more compared to the difference in delta omega. If I take these 2 points here. Similarly, if I'm taking these 2 points here, it's almost delta omega, change in the omega is almost 0, but change in K is there. Means this K, delta K is increasing and this delta omega is decreasing. Means your Vp value is decreasing. At one point when this value got saturated, this Vp goes towards 0. Means your signal is stopping at that particular frequency. This frequency is known as asymptotic frequency. So your signal is considered as a slow wave signal here. And we can utilize this property now. If we want better propagation, we can work in the lower frequency band here. If we want a concentrated electric field or concentrated signal in my structure, we can move towards the asymptotic frequency. So this portion of this dispersion diagram can be utilized for sensing purpose, and this can be utilized for the waveguide purpose. Okay, so quickly I will go through this spoof surface plasma. Generally, this negative permittivity of metal is coming at high frequency spectrum. It is not available at terahertz or millimeter or microwave hertz. So Pendry has given an idea that if we are engineering this metal surface with certain arrangement here, we can change the permittivity of that metal. Means your plasma frequency can be bring down here to the lower frequency here. Then when you can utilize here. So certain transmissions line structures are given here. See here. They are offering better transmission property, better isolation property, and isolation and transmission you can see here. This is light line, means your free space propagation. The wave momentum of this free space is very different from the wave which is traveling in the metal dielectric surface here, surface one. So if any free space signal trying to enter in this metal dielectric surface here, it's very difficult to interact here. So that's why the signal integrity is more here compared to the microstrip line. Okay, so crosstalk scenario will be low, signal integrity will be more if we are utilizing such kind of transmission line. So here, as we know here, we have drawn the dispersion diagram of this one here. Based on this, we are creating the spoof transmission line. As we know, the wave momentum in this cell is different from the microstrip line. Why we are using this transition? Because we know in our VNA, because you want to utilize these transmissions lines or your sensors using VNA for the measurement point of view. In the VNA, coaxial connectors are there, and along with that coaxial, you have SMA connectors. So those are sending TEM wave, and here you have only the TM mode here. So there must be a matching profile here. Impedance matching should happen. Then only the signal will travel from your VNA towards this structures here. So section 1 is your matching structure here. So your SMA connector will come here. The signal will come. It will slowly match with the spoof surface plasma transmission line. So you can see here, it's given a scenario here. And the transmission S parameter is showing a better transmission here. One idea you can get here, which solves many problems at high frequency. You can see here in the normal microstrip transmission line, the signal is mainly between the signal lines and the ground here. Your signal strength is more in between the dielectric substrate here. So the dielectric losses will be more along with the metal loss. But in this case, your signal is trapped between the metal and dielectric one here. It's not going towards the down lower conductor here. So dielectric losses will be less because your signal is not traveling throughout this dielectric one here. It's only traveling along this interface here. And you can see here to show the applicability of such kind of transmissions lines at high frequency compared to the normal microstrip transmission line. See, both transmissions line are separated with the same distance here, and then mutual coupling coefficient is being calculated here. So S41, it's better in this dumbbell shaped SSP line compared to the microstrip line. Okay, so crosstalk possibility is low. You can again refine. So it is shown in the terahertz range. As I told you at the starting, most of us don't have the measurement facilities. So what is the idea here? In the simulation, you can show it at the terahertz one. Then you can scale down your structure for the microwave frequency region, and same is being done here to represent at low frequency the structure is built, and then the same scenario is here. Okay, another kind of transmission line is given here with different shapes for more concentration here. So if your dispersions line for the spoof transmission line is going much away from the transmission line, and it's saturating very early, then you will get better field confinement here. Better field confinements means better isolation property, better crosstalk property here. So such scenario is given here. Because of time constraints, I'm quickly going through these things here so that we can finish within 5 minutes here. So again, structure is scaled up here for the microwave measurement scenario. Okay. Now we are utilizing these structures for our sensor point of view. Like our talk is basically on microwave means terahertz imaging, means sensing and imaging here. So how to get the sensing properties? If we want to interact with any material and we want to know what is the electric property of that one, then my electric field signal should interact with that material. If we are interested to know what is the permeability of that material, then my magnetic field should interact with material to get to know this new property here. Okay, so these field interactions should take place, means your field should be high enough, then only we'll get to know what is the permittivity or permeability here. So how to increase the field strength? Already we have seen that if we are working near to the asymptotic frequency, my field strength will be more. Or if you are not doing at that point, another idea is here that if we are like here, if we are creating any discontinuity here, like in this case, the signal which is traveling in this spoof line will have a different wave momentum when the signal will travel with this kind of spoof line. So there will be a mismatch here. So when there will be mismatch in the impedance as well as in the wave momentum, your signal will get trapped here. And when signal will get trapped, your electric field will get strengthened at that point here. So scenario is here when there is no discontinuity. This is the top of the structure. This is the bottom of the structure. The spoof line is getting signal from the top layer here, and then signal is traveling in this one here. So earlier when there is no discontinuity here, the only effect will come of the asymptotic frequency, because above the asymptotic frequency, there will be no propagation here. So you can see here, this is CPW line loaded with the spoof line here. So near to this one, spoof asymptotic frequency is there. So your signal is stopped traveling beyond that one. But in between, there is no dip here. But if we are creating this discontinuity here, such kind of scenario you are getting. You are getting a dip here because your signal get trapped for that one here. And if we are putting a sample here, dielectric sample, because electric field is there, which is more. So if we are putting a dielectric sample here, the field will interact with that electric samples and you will get to know what is the epsilon value of that one. Okay, that's the way we are doing here. We are changing the value of the epsilon, value of the sample under test here. Then we are able to know what is the resonance frequency of that particular point. We can create a model and then we can put an unknown permittivity sample here. And from that created model, we can figure out based on the measured resonance frequency here. You can also give the equivalent model, which is not necessary, but people are showing. So you can create electric model of it here. So you can see here, this spoof based sensors can help us to detect very low volume quantity here. So it is helpful for the biological sample detection here, because we are able to create, because in the microwave you are using metamaterials, CSR, SSR for this field concentration here, but at that time the size is more, so the sample you are loading over those places it's more. Okay, but when we are talking about the biological or any kind biomedical imaging, at that time we are not putting more sample volume. It's always in microliters here. So in that space, are we able to put it here? And in that small space, is my field good enough to interact with my samples? That's the challenge here. So spoof based sensors can be helpful at that time. So one scenario is already mentioned here. Another scenario in this spoof line, If we are creating a cut, when we are creating a cut means we are creating a capacitance between two plates here. That will give the resonance condition. This metal plate, metal will give the inductor part. This separation will give the C part. Accordingly, we will get the resonance condition. One is not help sufficient resonance, so we are creating two slots here. Based on that one, you can see the electric field concentration is at that place here. So we can put the samples here, then we can detect the change in the resonance frequency. Based on that one, you can do your measurement here. For the measurement, you can scale down your frequency of operation, means you can scale up your structures. That's it. If any question is there, you can ask.
Participants, if you have any query, you can ask. Sir, for these sensors, do we need to calculate the performance of the sensors, like the sensitivity or figure of merit or any other parameters?
Yeah, definitely. How are you going to compare the performance of your sensors with the already given sensors? There must be some parameters based on which you can claim that your sensor is good enough for that particular application. No, so you have to figure out what is the sensitivity. So sensitivity, you can define what is the change in the resonance frequency when I'm changing the permittivity value here. The more change in resonance frequency compare a small change in the permittivity will be a good sensor.
Okay, sir. And how we can measure this, sir, error of tolerance in the sensor?
Error of tolerance, you have to see what are the factors causing the error here. You have to take into account whether your sense bending is strict bending scenario. You have to take how much tolerance is there, to how much bend you can tolerate here. Tolerate means always the error should be less than 3%. So by bending a certain instance, whether your error remains in that band or not, you have to check it here. Whether your sample holder is kept at the exact place every time, when it is shifting, how much error we are getting here, so how much shift we can afford.
Okay. Shift means we have to
Like
concentrate
here
on
in
the
this case,
shift.
if you can see this slide, are you able to see it?
Yes, sir.
So you can see here this sample holder is placed at that point here. If it is not fixed properly, suppose during your fixation here, no, if you are fixing it here and because of human error you have shifted a little bit here, so the scenario may be here that your sample is not exactly at the middle points where you want. It is a little bit shifted, so now the electric field is less at that part here. It will interact less at that time. How are you calculating here?
Okay, sir. Got it, sir. Sir, one more question. Is it compulsory to calculate the normalized sensitivity or any sensitivity is enough?
Any sensitivity will work, but it's better to make it normalized, because at that time it is free from all the environmental factors.
Oh.
So comparison is good if you are doing it in normalization.
Any
The
more
reason I can
question?
told you here, like if you are plotting the reflectivity plot here of such thing, if you are not doing normalization, then there will be difficulty on the visualization side here. Like here, so here it is being normalized with respect to the normal skin here. So with respect to the normal, if there is a change in the burn side, you can easily detect it here. But if you are not normalizing it here, the color map will be different here. It will be difficult. So whatever maximum reflectivity you are getting, based on that one you are doing here. See, Q factor, each quality factors is generally responsible to detect the loss part here. The epsilon is having two parts, real part and the imaginary part, epsilon dash minus g epsilon double dash. The quality factor of the sensor, if it's good, then more accurately it can detect the loss part, upside and double dash. If quality factor is not good, then the detection of upside and double dash will not be good. Figure of merit is another way to represent your data. Quality factor is important parameter. The quality factor of your sensor should be good enough. I'm telling you in a very loose sense here. Come to the sensor here. This is your sensor you have designed here. If this peak you are seeing or the resonance, if it is not sharp enough, sharpness will define your Q. No, Q is your what is the FR value here, and then what is the bandwidth here when there is a change in the 3dB here. So if it is not sharp enough here, then if a small change is happening, you will not be able to detect it here. No, like if it's a kind of very flat one because it's zoomed one here, that's why you are able to see it here. But if you're, let me get here to the pen. And if your response is like this, sharp enough, and if your response of your sensor is flat enough, if there is a small change, you will not be able to detect it at all because you are not able to detect this peak correctly here. But in this case, you will be able to detect it here. So this sharpness tells about the Q, and it helps us for better detection. And when you are quantifying it, the Q is directly helping us to determine this upside and double as well. FR value is helping us to determine the real part of the permittivity.
Okay.
Perturbation theory, you can explore that one. So according to that one, you can get to know that your quality factor is helping us to determine upside and double dash. Your FR value is helping us to determine the upside as well. It's a kind of perturbation when the sample is changing. A small perturbation in the field is happening. And because of that one, you are able to detect the property of your material.
Any more questions, participants? Sir, I think no more questions are there.
Okay. So can we close it now?
Yes, sir.
Okay.
Sir, we are very much thankful, sir, on behalf of AICT Academy and Department of Electronics and Communication Engineering, MNIT Jaipur, sir. Thank you very much for accepting the invitation, and the session was very much useful, especially the sensor part and all the parts that you have covered, the terahertz imaging. They were very much useful to all the participants, sir. Thank you very much, sir.
Thank you. Thank you.